I mean,
perfect.
Yes. Okay, yeah, that's me. Perfect, really good. Well, first of all, thank you very much for attending the webinar. It's a pleasure for me to start with the first session speaking. Okay, I'm Julio Vidal. I'm a head of R&D in Moses Productos. We are a small company based in Spain. 1 second, I'm trying to change the slide. Okay, a small company based in Spain, in Zaragoza, a city between Madrid and Barcelona. We are a company, but we are really focused on thermoplastic processing for the R&D, trying to innovate in these technologies to bring new products. We have also other different technologies, but we want to become an expert in transforming plastic components for industrial use, the use of recycled materials, recycling polymers, and more sustainable materials for different applications. Okay, in this case, I'm going to talk to you about the injection molding. First, I would like to start with the material itself. We are going to work with polymeric materials, but we can differentiate polymers in many different ways. Okay, one of the cases, or in here you can see different cases on how we can differentiate the different polymers based on their structures and molecular forces, or in the source. As we are going to talk about injection molding, we are going to focus mainly in thermoplastic materials. Okay, and all the technology can be used either for natural or synthetic polymers, crystalline or amorphous, as you have on the other side. Of course, we will have some differences, and I will try to appreciate them during the talk. How or which points should we take care when we are using natural bio-based polymers, because in those cases maybe there is some points in which we have to have more care just to reach our final product and a good quality product. Okay. Okay, it's not changing now. I don't know. I don't know why it's not changing the slide.
I'll try on my side. Is that better?
Yeah, perfect. Okay, when we are talking about the different polymers and how they behave during the injection molding, we need to have clear what are their physical structure and how do you change the mechanical properties through time and through temperature mainly. In this case, I have plotted, well, you have seen here a plot about how the amorphous and crystalline materials behave. You can see that in both cases we have a TG, but in the case of the amorphous material, TG and melting point are really closed, so it's really difficult to differentiate between one and the other. But in the crystalline case, we can see a TG, which means that the material is starting to, we can deform the material easily, and then we have the melting point. This is quite important to play with both temperatures. Melting point, we mainly need it in the injection phase, once we have the material melted, and we need to deform it to get the shape that we want. And then the TG is really important for degrizzalization. Okay, we need, or which properties do we want from our material. We need to know this TG in order to adapt the mold, or depending on the technology, other cooling processes, so that we will be sure that we have this phasing here. I have also give you a table of different materials, just for you to know something about the different TGs. You can see, for example, in polypropylene, -20 to -5 degrees, which means that if we froze this material, we will see this common material that we have in the house. If we put it in the fridge, we will see that the mechanical properties of this material will change. Okay, so this is really interesting, and it's really a visual thing that we can do all of us we can do at home. If we take some of polypropylene, we put it in the freezer, and we will observe how these mechanical properties and how the material changes its properties visibly. In the next slide, what we will, sorry, and I think it, yeah, okay. Here again, I wanted to influence you and talk to you about the different properties that we need to take into account once we are processing the material, okay, which is the rheology. This is a key point for, I will say, all polymer processing technologies, but even more for injection molding, okay. In the case, we have two different technologies, or well, several different technologies to measure the rheology, but we have rotational rheology and capillary rheology. Okay, in the case of capillary rheology, it's a technology really used in injection molding because the flows and the shear rates that we are obtaining are really high. So that allows us to observe and try to understand how the material will behave once going through the nozzle and through the mold. This is really important in the case of bio-based materials because they usually degrade easier than fossil-based materials, which means that we need to fully understand how this process is done. And for example, in the case of PLA, which is a bio-based material, is also really important, not only because of how the material will behave during the injection, but also about the contractions that material will suffer in the mold. You know, when you cool down a material, the final volume, the density of it changes, and that happens also to the polymers once we froze them in the mold. But to keep on with the different examples in the next slides. Okay, here you have some advantages and drawbacks of the plastics. Okay, why should we, or when can we use the plastic and other materials? What do a polymer will offer to us? Freedom of design, low specific weight, reduced process cost, integration of functional components, low thermal and electrical conductivity. Problems, we have the tolerance, limit service time, structural responsibility depending on the polymer is not feasible. So once we think about using injection molding and polymers, we need to take into account these properties, and also the transformation technologies that we will see in the next slide, because it's not only the polymer and the plastic, but in the following slide, what we have. Yeah, that plastics have been growing and growing during time. During the last decades, they have grown. It seems the latest data is from the COVID pandemic, so has reduced. But in the following slide, you will see that only it's Europe, the area that has reduced the use of material during the last 5 years. Okay, you can see here how the overall growth of plastic in the whole world, but in Europe specifically, this has decreased slightly. Studies say that it has mainly been stabilized and a slow decrease. So we are focusing more on recycled material and bio-based materials, but also reducing the amount of plastic. In the next slide, you will see that what we have done in Europe is more than reducing, which has been reduced by 2 million tons per year, change the use from virgin raw material to recycled. And in here also, it's important in this virgin plastic use to introduce also the bio-based components, which in this case I have not been able to find official data, so I have not put it in here. But this will also be really interesting how Europe has not only going to recycling but also into bio-based, reducing in this way the environmental impact. In the next slide, I already start to focus on the different technologies that we have. I will go more in deeply to the injection molding, but for you to keep in mind that we have some other technologies, 3D printing, rotomolding, film blowing, thermoforming, and in most of them, the key parameters that I have mentioned in terms of temperature, TG, and melting point, and in terms of rheology, the viscosity of the material is key for the processing of these polymers and to obtain a good product. In the next slide, we already see some cases in which injection molding is competing with other production processes, such as extrusion blowing. Okay, in this case is injection and blowing to manufacture bottles. You can see in all the bottles that you will have in the house, if usually at the bottom, if you have a dot, it means that it's being manufactured by injection blowing, and if there is a full line, it will be through extrusion blowing. Okay, but for you to differentiate all the different technologies that we can have or use in polymers, and of course in bio-based polymers. In the next slide. Okay, we go already in depth in injection molding about the machine. We can work with many different brands. I have summarizing here some of them, and also in many different sizes of products. We can work with small products in which we will use a clamping force of 10 tons, or we can use to go to, let's say, a bumper from the car, or a container lid, which is parts with more than 1 meter or a 1 square meter area, in which we can use injection machines up to 5,000 tons of clamping force, which means that the amount of products that we can manufacture is huge. Okay, through injection molding. Only thing is that injection molding limits the design, and we have to go through, let's say, simple designs. We cannot go to complex hollow structures in order to manufacture a part. In the next slide. Here I have just summarized for you some of the limitations that we can see in the injection molding, and I was already mentioning clamping force. Okay, this is a point more than limiting because we have a huge range. We need to define what is the clamping force of our machine in order to see if we will be able to produce a part or if we will be able to produce this part. Okay, the salt weight refers to the amount of molten plastic that we can fit also in our machine. Common rates goes from 1 gram to 10 kilograms. Here in our facilities, we go to even more than 10 kilograms, but again, it's a limitation of the equipment, and it's really important to keep it in mind during the injection design of the injection part. Okay, design of the part. Then we have the maximum volume capacity of the injection unit and the mold size. Of course, we need to adapt everything to the machine that we have in the house. Otherwise, it will not be able or feasible to do it. In the next slide, what we keep going with the injection molding is about the different products. Okay, we can have limitations, but those limitations are more on the machine than on the technology. Of course, I said we can go to simple parts or simple structures, but the freedom of design is quite big, and we can have injection molding part in domestic appliances, bottles, everyday use, toys that we use in the automotive, outdoors, furniture, TVs. So you can see that really this technology is used in many different sectors, and that we can have products in our everyday life that are produced by this technology. In the next slide. Okay, the process itself depends heavily on the mold and the manufacturing of the mold and the capacities that we can have, and these gadgets that we can industrialize on how we can manufacture this flexible mold. Okay, so this will be a limitation, as I have already mentioned, and I will keep mentioning in the next slide. If we can go on, because it's key to manufacture the part, but it's also key to extract the part. Okay, this extraction is done in 2 different steps. One is the mold, in which we push the part outside of it, and then we have to take it from the mold and move it into the next stage, either if it is just to assemble it or just to take it out for other movement. In this case, the automation of the process is being the key, and today's systems, robotic systems, are being the next step into the injection molding. Okay, next, this doesn't change between bio-based or bio-based or fossil-based, but there are some points in which it's necessary to adapt the material, such as in the simulation. Okay, before we manufacture the mold and we work on the on the part itself, it's important to simulate and to study how the plastic and the polymer will behave during the overall process. This will give us an idea of those areas that are going to be critical, thickness, temperature flows, viscosity. We need to have some information before, but thanks to the simulation, we can avoid many different problems during the execution phase, and we can limit the amount of time that we spend in bad parts, let's say, or in optimization of the process, so that once we start the manufacturing process, we will go on directly into obtaining the desired quality. In the next slide, I also mentioned some alternatives that we have. We are working, or the general webinar is focused on bio-based materials, and this is something that injection molding is adapting to. Okay, mainly for PLA, bio-PET materials. The demand for sustainable materials is huge, and it's also been huge in the injection molding manufacturing technology. Main point for us in this case is that there is no need for huge adaptations in the injection molding. It's more a matter of small modifications in the mold to adapt for the material, in the temperature profile to adapt for the needs, and avoid degradation of the material in the SKU, so that we will obtain a quality part in the end. And of course, also for the design, keeping in mind the final mechanical properties that our material will have. So mainly it's quite similar, but only these points about the behavior of the material are the ones that we have to keep in mind if we want to produce a good quality part. In the next slide, the other alternatives is lightweight materials. Okay, in this case, injection molding is trying to increase the efficiency of the process and the efficiency of the material, so that we can go to less weight, which in case of the transport sector, which is one sector that is really using injection molding, is a key factor in order to obtain a more efficient automotive place, or a car transport in general. In the next slide, high performance materials is not only about weight, but also about the materials themselves. In the case of the bio-based material, this is also really interesting, how we can reinforce these different materials in order to obtain the mechanical properties that we want, and how this reinforcement will affect the injection molding process. We have to keep in mind that, for example, if we are going to use fibers to reinforce the material, these fibers will not be melted during the injection phase. So we need to fully understand what's the behavior of the fiber and the interface between fiber and plastic, in order to predict these final properties. Also, this is why a key point is the simulation, trying to understand how the material will behave in the mold, how it will flow, and which is the direction that the fibers and material, the crystals, also will obtain during the injection process. In the next slide, I also talk about reinforced materials, but in this case, I want to talk about a full textile, okay, that we can use also to over-inject the material and to improve, drastically or change drastically the mechanical performance. In this case, we can use carbon fibers, such as in the picture, but we can go also to bio-based fibers. I will try to speed up a little bit. In the next slide, here you have the injection machine as an overall. Okay, we can differentiate different parts. The injection part, in which we have the screw, which is on the right of the screen, and then the mold side, which is on the left, with the clamping force and everything. The idea is that we will melt the material in the injection side, and then transfer it through the nozzle, through the die, okay, into the mold. And here, huge forces will be applied into the material, and that's why we need to understand really well how the material will behave in terms of viscosity and temperature. Once we have that, the material will fill the mold, and it will cool down in there. In the next slide, I think I just summarize everything, but here you have the injection unit, okay, with a feeder in the middle. This injection unit allows the screw to go back and forth in order to push the material into the mold. In the next slide, we will see the other part of the injection mold, the injection machine, which is the clamping unit, in which we have on one side the mold, and on the other side we have this piston that will force the mold to be closed at all time. We need to understand that the material is going to be injected at high pressures, and we need some force on the opposite side, avoiding the mold to open and providing the nice form, that shape of the product that we want in our final product. In the next slide, here you have some the whole part. You can see the size of some of the some of the injection machines that there are available. By seeing what this person, just in comparison, we are talking about molds that can measure up to 2-3 meters. So really the clamping force, the clamping unit that we need to apply in order to obtain this is huge, and that's why we were talking about this 4,000 tons clamping force. Next slide. This is the cycle of the injection. This does not change if we go from a fossil-based material to a bio-based material, but what changes is the amount of time that the material should be retained into the screw during all this process. Fossil-based materials usually are more resilient than bio-based materials. This means that in order to properly inject a bio-based material, it's usually better to reduce the injection cycle and to adapt the dose that we charge into the screw as much as possible to the dose that will be used in the final part. In the case of the fossil-based materials, in some cases, you can fit more material into the screw and keep the material in the screw melting and molded and at those high temperatures. In the case of bio-based material, it's better to make the injection faster and try to avoid this degradation in this sense. Of course, it depends on the material. Okay, I'm talking generally. In each bio-based material, it will be important to understand how the polymeric structure will behave during time and how temperature affects it and its final mechanical properties. In the next slide, we have some times that I was mentioning how the different cycle of the injection is divided. Usually the process starts when the mold is closed, then we forward the injection and we go with the injection. And this, once the material is started to get into the mold, it starts to cool down, and we go with the dwelling injection backward, which means that we are feeding again the screw, and we are preparing the screw for the next injection while the plastic is in the mold cooling down and in order to extract the part. You can see that most of the time using the injection cycle is not for the material to be in the to be injected, but to cool down the material in order to extract it from the mold. And as we prepare the material as the first phase in this cooling phase, it's quite important that we reduce the cooling phase as much as possible so that we reduce the degradation of the material that is in the mold. Next slide. Here again about the injection, we put the material inside the mold and we extract it while we are charging. Again, we can go this through, as I think I have already passed my time. We can go to the next slide because we have already mentioned this point. I want to mention about the geometry because it's really important to understand the material flow in order to design a mold properly. We usually it's quite important in the case of injection molding to avoid edges, okay, and 90-degree angles. All angles usually are smooth in order to allow the better flow and avoid any problems or gases that are accumulated in these corners. You can see here how the material flow changes with corner or without the corner. And it's really important to keep it in mind during the design of the product and the design of the experiments that we will obtain. In the next slide. Okay, the cycle that is done in the mold is, I think we have already mentioned it, but we cool the part, we provide the structure, supply system, movements, performance, and expulsion. All of these should be keep into account as the cycle of the mold is going. Similarly, is equal in the case of bio-based materials as in the case of fossil-based materials. So in the next slide. I started to go into different technologies that we can use in both cases, fossil-based and bio-based. One of them is gas-assisted injection, in which we have physical and chemical gases that can be explored. Usually with bio-based materials, I have seen more the case of the chemical ones. That doesn't mean that we cannot go physical, but the entrance of this gas into the mold, it means high forces that can degrade the material. That's also maybe one of the points, as I have mentioned, the bio-based materials, they have a lower range of work and it's easier to degrade them than fossil-based. So usually the industry is moving into chemically formed materials in which we can obtain this product that you can see in the screen. In the next slide, you will see other potential things that we can do with injection molding, and of course also with bio-based materials or fossil-based materials, which is over injection. Okay, in this case we can over inject a metallic part. We can over inject a label, okay, with AML technologies, in which we add the label into the mold and afterwards produce the injection process, so that the final label will stick into our product. Other case that we developed in our facilities is this a hollow structure in which we 3D print it apart, over inject it, and then remove this 3D printed part in order to obtain a hollow structure, which will be impossible to do only by injection molding. So the key in this case, and it's possible to do with fossil and bio-based material, is to combine the different technologies or how we can adapt everything. In the next slide. Yes, some of the products that we have and that we are producing, but as I go over my time, I will not talk to you about it. Just if you want to try to produce a part, just keep us in mind and contact us, because maybe we can try to help in this sense. With bio-based materials, we have a great expertise, and for sure we will be happy to help you in the production of this part. Thank you very much.